Hello, Tommy.
Hello.
We are live. We don't have any attendees just yet. Let's give them a moment. I can see folks dialing in now. But 7. Numbers are climbing. That's good. Let's give it a minute and then get started. I can see the numbers steadily climb here, Tommy. So let's just give it one more minute. And let's get started. Right. So let's hit 3 o'clock here. Shall we get going then, Tommy?
Yes, let's do that.
Alrighty. Okay. Very good afternoon, folks. And thank you all for joining us today for another Spotlight webinar. I hope you're all keeping safe given the current circumstances. I'm super excited to be here to present our new white paper, the cover of which you can see here on the slide, on raising recovery rates in real time using in-well fiber optic sensing. The paper is due for release next Monday and details how an oil and gas operator can use LYTT's hybrid analytics software to convert an often unused piece of equipment in a well, i.e. a fiber optic cable, into what we call downhole production observatories, enabling real-time monitoring of production events. The technology has now been deployed across multiple assets to not just monitor real-time downhole production changes in fiber-equipped wells, but also dynamically boost the production profiles in these wells, adding around $400 million of production benefit to our customers' bottom lines in 2019 alone. I'm here today with Tommy Langnes, the other co-founder of LYTT, who I've been on this journey with since the initial inception of the idea back at BP. Tommy, would you like to say a few words?
Of course, and thanks for the intro, Brad, and good afternoon, everyone. I'm also super excited being here today to evangelize LYTT's great progress in fiber optic reservoir performance monitoring. I got background from various wells and production engineering roles in oil and energy companies like Norsk Hydro, Shell, and BP, where I also wrestle with production optimization challenges. In 2012, I brought my family from Norway to the UK to take on a job in upstream technology in the team in BP. And that's where I got introduced to distributed fiber optics technology, a handful of business problems in BP to be solved, and also Pratt. And I think that was the beginning of a very special journey.
Great. Thanks, Tommy. Right, we'll kick things off with an overview of the business challenge and how in-well fiber optic sensing, when combined with hybrid analytics, can help not just overcome some fundamental surveillance challenges in the oil industry, but also generate production boosts using dynamic well optimization methods unlike ever before. We'll then provide a sneak peek of the machine learning analytics that underpins the pattern recognition software that enables this transition, followed by some real-world examples of how the application of this technology has translated into substantial production benefit to field operations for our customers. The session should last around 30 minutes, and we hope you enjoy it. All right, over to you, Tommy.
Thanks, Brad. Well, hey, there is a significant opportunity in subsurface optimization. All oil and gas field operators, they are continuously attempting to increase production, reduce cost, improve safety on their assets. And a systematic approach to maximize economic recovery could generate improvement of recovery factor as much as 10% and unlock substantial value. In complex water flooded fields, the number could even be higher. Production optimization allows operators to increase productivity from existing fields and would include several technical areas of interest. The value contribution can come from different technologies. Production optimization will typically need advanced and intelligent well completions, which can provide real-time data, potentially from a fiber optic monitoring system, and the capability to reconfigure the well architecture without well intervention. System should also be able to collect, transmit, and analyze reservoir production data, and to prove completion's integrity, and to enable remote action to better control reservoir, well, and production processes. These systems generate a large amount of real-time production data, and the key challenge is to realize direct added value to the operations. A typical practice today is to assess well performance, or in order to assess well performance, is to acquire production logs, which represents a snapshot in time measurement. And these logs are taken infrequent, at best every 2 to 3 hours, and even less frequent if we talk about offshore and subsea wells. Oil fields, reservoirs, and wells are becoming more complex, require improved time resolution to understand the dynamic changes happening in the reservoir, flow contribution from multiple zones, etc. Production logs also involve huge amount of resources to acquire. So this could be time, people, equipment, and so on, and introduces also logistical challenges and HSE risks. It requires stopping production, intervening wells introduce risk of getting stuck and losing piece of tool string in the hole, and even sometimes hole access prevents to perform any logs at all. And even with successful intervention, inflow profile from conventional logs may not be representative, depending on what type of completion you have. All these risks and complications usually turns into inefficiencies, production deferrals, and in consequence, far larger OpEx than anticipated for a number of our clients. When we began asking subsurface engineers what information would benefit them the most for reservoir performance optimization, the first answer they gave us was the need for more frequent production logging. And then we asked them, when do you need that? The answer was usually tomorrow if possible. However, getting this information frequently through interventions is, as you can understand, quite expensive and challenging. So that's when we formulated the 24/7 production logging idea using the fibre as an alternative. We began by painting what we thought would be the ideal scenario based on our understanding of the challenge, which is to have production logs, not just once in a few years, but get this live every second, almost like a CCT downhole within a well. This seemed like an impossible task at first, but we turned the visual thinking into our vision and also an aspiration, which we shared with our clients. And now we have this capability in real time. We began by testing the concept with our clients, and it didn't take too long before we got some traction for the technology. So where we are now, no quarterly or monthly logging, but actually providing our clients with 24/7 real-time inflow profiling, which is production log every minute by using in-well fiber optic cables. This has been proven to be extremely valuable to our clients, as our customer can now not only make long-term decisions around well target selection and field development decisions, but also daily production optimization. So in essence, this means no cost of running tools downhole, no HSE and execution risk associated with interventions, no interruption to production. You can free up rig time to drill and work over wells, reduced OpEx. So basically what you need is a laptop and internet access. Don't even need to go to the office these days.
Absolutely right. All right. Thanks, Tommy. Before I jump in and discuss the algorithms behind our production management app suite, I think it'd be useful to quickly refresh what LYTT's differentiated offer is and how our real-time apps that we will talk more about in the coming slides sit within LYTT Live, our cloud-based data platform. What we offer in LYTT is an integrated cloud-native software that enables real-time identification and classification of downhole production events using distributed fiber optic sensing data. Starting from left to right in the image here, we have fiber optic cables that are deployed in well as part of the well completion. These fibers are then connected to optical interrogators on the surface, usually for distributed acoustic and temperature sensing, DAS and DTS in the image, that convert the optical data into acoustic and thermal profiles along the length of the fiber. For those who are familiar with DAS or distributed acoustic sensing, you would know that one of the biggest challenges with DAS is big data. Each DAS instrument typically generates acoustic data of close to 1 terabyte an hour. That is nearly 1,000 movies worth of data acquired every single hour from each and every sensor. LYTT software starts from what we refer to here in the image as the RTPU, the real-time processing unit, which is an edge computer running LYTT's proprietary real-time feature extraction software that intelligently distills just the most relevant features in the acoustic and thermal signals in real time. This reduces DAS data volumes at site by over 1,000 times without, and I repeat, without, losing the most relevant strands of information required for patterning multiple in-well fluid events, almost like finding a needle in a haystack. This feature-rich dataset is then streamed into our cloud-based streaming analytics software that transforms these features into user-friendly logs using LYTT's proprietary hybrid analytics-based pattern recognition models. Think of this as the layer where we convert the acoustic feature data into something more meaningful for the end user, like a downhole sand log or a flow log, using specific algorithms that we refer to as apps. These logs are then presented to operators in near real time, sometimes alongside other peripheral sensors like choke or downhole pressure, in a time synchronized fashion to help operators make effective decisions in real time. A key take home here is that we don't just present acoustic data, but the insights as flow logs or sand logs in near real time, contextualized with other sensor inputs that can then be used to inform faster, safer, and more confident operational decisions. The solution we offer is setting a new standard for wells optimization, wherein the operator no longer relies on outdated production logs to make operational decisions, as is done in most cases today, but uses real-time production information across every meter along the reservoir to drive dynamic optimization decisions unlike ever before. We now have around 100 patents filed on the backend data infrastructure and the underpinning analytics, and have now deployed the system across over 170 times across multiple assets around the world to deliver huge production gains by aiding smarter decisions in real time. Now, the question I often get is, how can we recognize the patterns of the acoustic signals for these different events to be able to differentiate between gas, water, sand, and oil? We talked about this at a high level in the last webinar, but let's go into it in a bit more detail here. We use what we refer to in LYTT as hybrid modeling, where we use a combination of machine learning and first principles physics to pattern and define signatures of different fluid types. We started off by trying to build what we often refer to in data science as a supervised learning model, using techniques similar to those used in the music genre classification industry, almost like designing the Shazam app, but for oil and gas well surveillance instead. We began by collecting training or labeled data to study the acoustic and thermal profiles made by different fluid types as they influxed and moved around in the pipe. We did this by designing a flow loop experiment where we mimicked a typical well completion design and instrumented this with fiber optic cables. We then ran hundreds of experiments simulating real-world reservoir conditions and acquired DAS data to better understand what each of the fluids actually sounded like under different scenarios. What we observed was quite interesting. We noticed that the same fluid type could make very different acoustic patterns depending on a number of factors, like the completion type, the fiber location, and also the background flow itself. So we began patterning these signal variabilities to capture the signature envelope for each of the fluid types. We didn't just stop there. We took it one step forward to then reason why we see the signatures we are seeing using first principles physics. We then used both of these information sets to design hybrid rules that not only took into account the signature variabilities as captured by our machine learning models, but also knowledge derived from first principles physics that were then used to calibrate the machine learning predictions in real time. This forms the fundamental basis for LYTT's algorithms that underpin the production management app suite that we offer today. The approach helps overcome some of the fundamental challenges in using the technology, enabling better calibration of lab-to-field data, modeling for well-to-well variabilities, and also overcoming some of the signal uncertainties and improving confidence with fiber measurements. Okay, now let's see the pattern recognition framework in action for inflow profiling. What you see here is real field data where inflow logs were computed using LYTT's hybrid analytics models applied to DAS and DTS datasets that were acquired in a fiber-equipped well. As Tommy mentioned before, one of the biggest surveillance challenges for well optimization is being able to understand what the flow contributions are from each of the producing intervals in the reservoir. We realized that arriving at one algorithm for inflow profiling as a whole could be quite challenging. So we started off by chunking the problem into smaller pieces. We realized that the challenge here was to address three fundamental questions. One, where is the inflow coming from? Two, what is the fluid type? Three, how much of each fluid type is influxing? So we built 3 model classes, one for the question on where, one for what, and one for the how much. What you see here on the left is the inflow detection map. It represents the signals made by the inflowing fluids captured using hybrid analytics applied to both temperature and acoustic data in a well that had 3 producing zones, zones 1, 2, and 3 in the image. We see choke at the bottom in red and the dynamic inflow of fluids presented as a heat map, with depth along the vertical axis and time along the horizontal axis. The second image answers the how much question and gives the relative percentage allocation of the volume of inflow across each of the producing intervals. The third image shows the application of hybrid analytics for phase classification to classify the different fluid types as they influx into the wellbore, answering the question on what. You can also see how the well's production intervals and flow dynamics are changing as we ramp the well up, giving clarity around not just where the fluids are coming from, but also when each of the zones come into production. This is an extremely important question to answer to really get an understanding of the flow dynamics in a well, and is something fiber optic sensing is uniquely placed to address. Unlike traditional intervention-based logging techniques, having a fiber in a well enables passive surveillance of what happens in the wellbore during production, which when clubbed with our hybrid analytics methods, provides real-time insights into what the changes in the flow dynamics are as we operate the well. In this example, the dynamic variabilities observed were used to understand where and when water broke through in the well. This insight was then correlated directly to the drawdown pressures applied at the time of water breakthrough and used for real-time optimization of the well. This led to an instant boost in the oil production rates, increasing the overall production profile in the well by several thousand barrels of oil a day, while significantly reducing the overall water production rates. The technology is now running live as we speak, streaming real-time production information from an offshore asset, and has already been used to implement the first ever fully fiber-informed water shutoff operation, the results of which will be presented at the upcoming SPE ATCE conference. Next, let's see an application of the technology for real-time downhole sand monitoring. Sand management remains one of the key production challenges in the oil and gas industry. This is because many of today's highly productive fields comprise of weakly consolidated sandstone reservoirs. What this means is that as we produce oil and gas from these types of reservoirs, they quickly disaggregate and produce sand along with hydrocarbons. Sand, as you may know, can be quite erosive, and at high production rates, sand tends to erode the piping in the well, causing well integrity risks. If it is established that the well is consistently sanding, they are often choked back to minimize sand production. This, however, implies that the well's production performance also gets a hit. This may mean an offshore well that has been set up to produce higher rates of oil eventually may end up producing just a small fraction of what it was supposed to, consequently resulting in pretty significant production losses. Most operators today tend to take surface measurements like sand samples or use acoustic sand detectors to identify sand presence. This, however, gives little to no indication of where the sand is actually coming from, which is a key question to answer if we wish to fix the issue. This therefore requires surveillance downhole and not just the surface. This is where LYTT's technology comes in. We use LYTT's hybrid analytics to answer 3 questions. Where is the sand coming from in the well? Which reservoir section? Second one is, when does the sand get produced? And third, how does the sand propagate within the pipe? All just using a single fiber deployed along the well. What you see here are results from the use of LYTT sand monitoring app for profiling the influx and the transport of sand in a fiber-equipped high-rate oil well. The image on the top left presents what we refer to as a sand log. It represents the output of a real-time sand app that isolates and captures the noise made by sand on entry into the pipe, enabling clarity around where the sand gets produced. These logs are computed every second and presented alongside contextual information, as we explained before, like choke and downhole pressure, all in real time through a cloud-based web interface, enabling dynamic optimization decisions. In this instance, the results of the sand app were used to identify and remediate sand-producing intervals using mechanical expandable patches. This enabled a reduction in the overall sand production by over 80% in the well, and an increase in the oil production of over 2,000 barrels of oil a day, as you can see from the image on the bottom right. Coming.
Thank you, Brad. Integrity of well barriers is one of the fundamental requirements for the safe operation and abandonment of wells. With increasing well age, complex well designs, and regulatory requirements, integrity challenges are becoming more complex, and new solutions are required to effectively identify, locate, and monitor sources of unwanted fluid flow. This could typically be problems like assessing cement barrier performance behind multiple casing strings or identification of pressure source for sustained casing pressure. Precise and confident diagnostics of well barriers help targeting remedial actions and provides valuable input to determine the well's risk level. The industry is also facing a huge liability addressing decommissioning of wells at its ends of life. This is a $100 billion problem in the North Sea alone, and the bill could double or even triple in the future. LYTT's well integrity algorithms have been used to identify tubing and casing leaks, flow behind multiple casing strings, packer leaks, formation seal assessments, advising setting depth on permanent lateral barriers in plug and abandonment wells, etc. Here on this slide, you can see LYTT's tubing leak detection app in action in a fibre-equipped oil producer. This well had developed a pressure buildup in a inlet above allowable leak rate and was subsequently shut in. The pressure behavior suspected a tubing leak. Multiple diagnostic runs with conventional logging technology, this being multi-finger caliper logs and acoustic point leak detectors, concluded a single leak point. The well saw 2 unsuccessful remedial attempts before decision was taken to trial DAS. The LYTT tubing leak app identified multiple leak points over 600 to 700 meters in the tubing at 25 bar differential pressure, strongly suggesting leaks through tubular connections over that distance. The well was, after 3 years of shut-in, successfully remediated with a coiled tubing insert string, recovering substantial production with no signs of any pressure buildup.
That's great. Okay. To conclude, fiber optic sensing, when clubbed with hybrid analytics, can transform fiber cables in wells into production observatories, enabling a fundamentally new paradigm of in-well sensing and providing real-time insights into well flow dynamics unlike ever before. These insights can be used to pattern multiple downhole events in real time, enabling 24/7 inflow profiling and downhole sand detection, as we've discussed, but also dynamic and distributed well integrity monitoring. These insights can be used to drive dynamic well optimization procedures without the need to intervene for well logging. And as Tommy mentioned before, this means no cost of running tools downhole, no HSE and execution risks, no interruption to production, and reduced OpEx. The technology has already delivered around $400 million of production gains in the oil field in 2019 alone for our customers. For further case studies or to learn more about LYTT's hybrid analytics software, visit lytt.com. And those on the call will also receive a notification once our white paper is due for release, which should help bring more of the value cases to life. With that, we open it up for questions. So if you have any questions, just pop them in the chat window there, and we'll try to answer as many as we can.
All right.
All right. Okay, I'm seeing a few come in, Tommy. I think let's just take the first one. How have you validated the flow profiling outputs? You want to take this one?
Yeah, happy to do that one. Well, recent deployment that we talked about I think it served as an excellent validation step, as the insights from the apps, they were used on their own to inform a targeted water shutoff operation. At this instance, post-water shutoff, the well drawdown pressure were double with no signs of any water inflow, concluding the accuracy of the model. The results will be published in the upcoming SB ATECE 2020 conference. We have also done some production logging blind test comparisons with excellent results, which also will be reported in due course.
Very good. Okay. There's one question from Andrew. Can you remind us of how frequently conventional logs are taken? And then how frequently can they be taken with LYTT's solution? Maybe this one's for you as well, Tommy.
Yeah, well, I think that hugely varies in what a geographical location you are, and also what conventional well type you are in. So offshore subsea, it could be as frequent as 4 to 5 years per production log run. Whilst at land or land assets more frequent. With the LYTT capability and with a permanent fiber optic cable installed in the well, you basically have it 24/7 all the time. So it is a transformational step change when it comes to wells performance monitoring.
Good. Okay, let's take the next one. What is the difference between intelligent feature extraction and simple data compression? Maybe something I can take, Tommy.
Yeah, please do.
Typically, with gas data, people tend to use lossless or lossy compression methods to minimize the data volumes captured at site. This is usually either by downsampling the data, which would result in lower frequency bandwidths in the data captured, or simply producing and storing FBE data, frequency band extracted data, that computes the energy within certain frequency ranges. Both of these have some obvious drawbacks. Simple downsampling methods mean you lose some valuable information that is often present at the high frequencies, and simple bandpass filtering would also mean the granularity required to identify variabilities in the patterns get lost. In LYTT, we extract statistical features that are representative of various downhole fluid events that we wish to capture, like ingress of gas, water, oil, or even regime changes like slugging. These are not just frequency band information, they're a proprietary set of statistical features computed from the raw acoustic and thermal data that are configured specifically to be descriptive of the signatures observed for each of these fluid types and events that we wish to capture. Generating such a feature set would obviously require an understanding of the signatures of the events of interest, which is what we have obtained by investing in hundreds of flow loop tests to simulate different flow and well environments. We have also conducted further calibrations through extensive field learnings and testing to better understand the applicability of these feature sets in the field, which has in many instances also led to an evolution and further calibration of the feature sets. This is quite unique to what we do in LYTT, and we see this as being some of the fundamental building blocks that we then build on top of and build algorithms on top of. Today, these features are extracted in real time from the DAS data using our edge analytics and then further processed and transformed in the cloud to extract the signatures that are relevant in real time and convert them into meaningful insights like sand log, leak log, and flow logs.
Good, Brad. I do see it, and there's a question from Osvaldo Garcia. How much data is being streamed onshore when monitoring in real time? Assume we need to account for specific COM specs. So this means a certain bandwidth, I guess, to transfer data away from the well site to cloud at the offshore platform. Brad, I think you have these numbers, huh?
Yeah, I can talk to it. So as I said before, with DAS, you're probably looking at about a terabyte per hour as far as the raw data is concerned. But what we try and do is, as we just described, we feature extract at the edge. And this usually reduces data volumes by somewhere between 1,000 and 2,000x at site. And this makes it far more consumable and also streamable, right? So when you have 1,000 movies, if you just think of Netflix, and if you have one movie streaming, that's something your bandwidth can easily handle. But if you have 1,000 movies streaming at the same time, it'll collapse, right? So it's very similar. So what we now look at doing is try and get about half a movie or 10% of a movie streamed per hour, and that's after the feature extraction. And we also push in some BTS-based features computed at the edge too. I hope that answered your question.
Very good. The questions there are just popping up here. So
yeah, there's this one which I think would be useful here, Tommy. So you mentioned the need for dynamic measurements and snapshots. Why do we need this for well optimization? Maybe you can talk about the power of dynamic measurements, Tom.
Yeah, that's a good one. Wells are truly dynamic and more dynamic than most people think. Dynamic measurements definitely provide you with a clarity around the changes in the well flow dynamics over time. It also helps you understand the changes in the flow resulting from various operational steps, really, like changes in pressure profiles that can be used for optimizing the well's production profile with full visibility of what is happening downhole. This has let our customer assess and pick the sweet spots to maximize the production. And these sweet spots, they are not always intuitive unless you have this granular piece of information and predictable, which is where dynamic measurements help you advising what the sweet spot and the optimization steps are.
Right. There's one on injection profiling, which I think is very pertinent. So have you used fiber optics for injection profiling? Maybe I can take this one, Tommy.
Mm-hmm.
Yes, the answer is yes. We are running our outflow app live as we speak on an asset where we provide real-time outflow allocations. The information here has been used to identify out-of-zone injection and also evaluate the cap rock integrity, and has been used to increase the injection rate and subsequently enhance the production in the field. Right, and then let's look at this.
There's one on from Swapan. How can you install fiber in legacy wells, or is it only possible for new wells?
Do you want to take that one, Tommy?
Yeah, well, that's an interesting one as well. So I do think that I think the largest size of the prize is if you can get the fiber across the reservoir. That's where you can really get into the full benefit of inflow profiling. So retrofitting the technology into existing wells, I think, is possible when you do a recompletion. But without the recompletion, it's going to be really hard to get a packer, and typically through a production packer device. So I would say technically possible getting a fiber down to the packer through the annulus as a retrofit solution. However, are you going to have it across the reservoir? That is also depending on the completion type, etc. But it's possible to get a fiber on the production tubing as a part of a recompletion and sidetrack.
Okay, I see another one, which is how many assets are you live on? So we're currently live on 6 assets around the world, streaming 24/7 insights from multiple wells per asset. Okay, let's just take one more, Tommy, in the interest of time. We've just hit 3:30. Okay, so there's this, I think this is a very pertinent one. This is around the use of DAS and DTS. You mentioned the use of DAS and DTS for flow profiling. Would the output be effective with just one of these, i.e. using DAS alone or DTS alone? We've seen that the best results in most instances come from a combination of DAS and DTS inputs, especially in multi-phase flow environments. DAS and DTS complement, we've also seen that they complement each other quite well to overcome some of the non-uniqueness challenges and signal uncertainties that we see with each sensor independently. And using them both provides us with an added layer of confidence in the interpretations. This, when presented with the contextual information that we aim to present through our visualization app, enables far more informed decisions as well, and helps dynamic well optimization, unlike you would do with conventional loading. Okay, I think with that we should close, given that we've just passed 3:30. There are a few more questions here, but what we do here is just take some of those questions and then perhaps respond back, Tommy.
Yeah.
Had the chance to
Let us do that.
Let's do that then. Okay, with that, we will draw the webinar to a close. Thank you once again for your participation, and have a great day.
Thank you very much.
Thanks all.